Right, and finally I'd like to invite up Kelvin Choi from Imperial College London, who's going to talk about developing an automated method to estimate spectrally resolved DNI for solar energy applications. Thank you, Kelvin.
Thank you. Hi, my name is Kelvin. I'm a first-year PhD student from the Grantham Institute at Imperial College London, NCEO. So today I'm going to talk about developing an automated method to estimate spectrally resolved DNI for solar energy applications. So I'm going to begin by talking about what are the state-of-the-art in terms of solar technologies are these days. And that will motivate us to think about why moving forward, it is crucial for us to estimate spectrally resolved direct normal irradiance, or DNI. And I will conclude the talk by outlining a couple of schemes that we've been developing to estimate these quantities. Now, to begin with, obviously we have to ask ourselves sort of the big question of why this is all important. And it all boils down to the fact that in face of climate change and the need to meet goals set forth by the Paris Agreement, there needs to be an aggressive move towards renewable energy. And in many parts of the world, solar technology is an obvious candidate. The state-of-the-art in terms of solar technology in solar farms are called multi-junction solar cells in concentrator photovoltaic systems, or CPVs. These technologies have been blooming in the past 5 to 10 years, and not least because they have amazing efficiencies, up to 30% in commercially available modules, and the world record is at 46% done under laboratory conditions. So that's pretty amazing, right? Almost half the incident photons get translated into pure, clean, green electricity. But there's a caveat to this number, and it's the fact that typical CPV modules are optimized and tested against a standard DNI spectrum at air mass 1.5 under a low aerosol optical depth condition. Now, what's the problem with this? Well, really three things. First of all, a standard DNI spectrum is idealistic. It assumes a fixed solar-zenith angle at 48 degrees, and most importantly, it assumes a low aerosol optical depth, which is actually not very representative of the actual climatologies in which many of these solar panels are deployed. So this is a standard AMRS 1.5 spectrum widely used within the photovoltaic community. And it's been shown that if we assume this fixed spectrum, there can be up to a 15% variation in annual energy yield estimation. And the reason for this is because unlike traditional single junction silicon cells, these multi-junction CPVs are extremely spectrally sensitive. And to illustrate this point, this is a typical sort of commercially available triple junction cells. So you can see at the bottom, 3 layers of sandwiched semiconductors with their respective band gaps. And the way these things work is that the most energetic photons get absorbed at the top layer up to the band gap of that layer. And photons with longer wavelengths will be absorbed by the layer below, and so on and so forth. So you can see each layer is specifically engineered to absorb a very specific slice of the solar spectrum. In order to achieve 30, 40% efficiency, like we saw just now, all the thickness and the doping of these materials need to be carefully optimized. And it's impossible to do any of these optimizations if we do not have a realistic sort of estimation of the photon energy distribution in the first place, and hence, spectrally resolved DNI. Another complication is the fact that these multi-junction cells are typically topped with a concentrator system. And these concentrators have very low optical tolerances. So just to put some numbers here, so the WMO define DNI as photons that come within a plus or minus 2.5 degrees cone. And this definition is inconsistent with, for example, the optical tolerances of a typical CPV system, so about a degree, which is again very different from, for example, photometers, ground-based photometers, and radiative transfer calculations if not treated correctly. So you can see there's a wide sort of array of inconsistencies in the way we sort of define, we report, we measure, and we apply DNI measurements, and it can easily lead to systematic biases. So with these in mind, it's suffice to say that if we're given a particular sort of climatology and want to optimize the cell design for that climatology, or we're given a particular cell design and want to ask ourselves where is the best climatology to deploy these solar cells, the quantity that we need is spectrally resolved DNI measurements. Unfortunately, these measurements are extremely and frustratingly limited, so we're sort of left with no option but to actually estimate these remotely. So, to conclude so far, so moving forward, we need to routinely estimate spectrally resolved DNI for solar energy applications. We have to do it in a way that's consistent with actual optical tolerances. And lastly, ideally, we would like to do all of these based on real climatologies and observations. Now, with these in mind, I'm going to outline a few sort of spectral DNI estimation schemes. And to validate these schemes, we have picked Santiago, Chile as our case study. Santiago was chosen because it has complex aerosol climatology. So there's a Pacific Ocean nearby, it's an urban industrial area, there's a desert, and biomass burning activities all around the place. And at Santiago, we have 1 year of broadband DNI measurements done using 2 pyranometers, so we use that to validate our schemes. There's an approximately co-located AERONET site that will give us aerosol optical depth measurements. And lastly, we will characterize the atmosphere using ECMWF CAMS analysis. And all these schemes, the key point is to properly account for the effects of aerosol. And to illustrate this point, this graph plots the differences in the simulated spectral DNI by varying the aerosol type in an otherwise sort of identical atmosphere. So you can see, and also overplotted are the spectral sensitivity of a typical multi-junction solar cell. So you can see around the region of the most energetic band gap, there's a substantial variation in spectral DNI up to 150 watt per meter square per micron if we do not properly account for aerosol in our estimation scheme. So, the 3 schemes. First, we call this a climatological aerosol scheme. So there's a baseline where we set a fixed a priori climatological aerosol across all our simulations, and that would be maritime polluted type for Santiago. The next scheme improves upon this, and we call this the spectral aerosol classification scheme, and we allow a selection of 1 of 9 opaque aerosol types for every single time slot. And the way this works is that AERONET observe AOD in these particular channels. We can also run simulation to generate what we call simulated AOD, so what the sensor would have seen. We can find a difference across the channels, add them up, repeat for each of the 9 opaque aerosol types, and select the one that minimizes the difference across all channels. And this way, this allows us to pick the aerosol type that has the spectral behavior most compatible with observations. So that's that. The last one is similar to the previous one, but we add this extra circumsolar factor, or CSF here. And this term accounts for all the considerations we're talking about in terms of circumsolar irradiance and optical tolerances. There's too much detail to go into, so I'm not going to go through them. But the key parameter here is the circumsolar ratio, which quantifies the percentage contribution of the circumsolar part to the direct total beam. And you can see around the most energetic band, there can be up to 20 or 20, even 30% contribution. And again, it depends on the aerosol type, shown in these lines. So these are the 3 schemes, and how do they compare? So we have run these schemes over Santiago for an entire year and compared them to in situ broadband DNI measurements, and here are the results. So the green line shows the baseline climatological scheme, so again a fixed aerosol type across the entire year, and you can see there is a negative 10% bias in the simulation. By doing spectral aerosol classification, we have sort of substantially reduced the bias, but it's only when we include also the circumsolar consideration that we achieve a 1.7% simulation bias, and this is well within the instrument uncertainty that was used, or the ground-based DNI measurement uncertainty. And at 1.67%, that translates to about 11 to 12 watt per meter square bias, and that compares very favorably, if not better than existing approaches. And it's given the fact that also, like Santiago, is actually quite a challenging place to simulate these things, because aerosol, but also the geology and the mountains and so on and so forth. So just to conclude, so we've developed an automated method to estimate spectrally resolved DNI for solar energy applications. This was done using spectral aerosol classification that take multi-spectral aerosol optical depth, and we've demonstrated the importance of accounting for circumsolar effects. Moving forward, we want to test these schemes in more locations. We also want to validate our spectral calculations, because all the validation we've been doing are in broadband. And this is quite hard, because these kind of data is not usually available. And lastly, we want to sort of use satellite retrieved AOD to enable a global assessment of solar energy resource. And that's that. Thank you.
Any questions for Kelvin?